Okay, so we've been kind of working up to this point, but I think that we can see that we can predict the pH now of a solution when we're given the concentration of strong acid or the concentration of a strong base. But now, because of our understanding of equilibrium, we can also predict the pH of a solution of any weak acid or any weak base. Okay, and that's what this chapter is about. This slide serves as kind of a review for us for equilibrium in general. Right, so here's a chemical reaction. And the reaction HA, where this represents some generic acid, interacting with water to form H3O plus and A minus. Right? This general dissociation of a weak acid can have a K value, right, or a K expression, and it will always be the hydrogen ion times the concentration of A minus over the concentration of our associated acid, how much is together. All right? So I like to write that a little simpler, where I just think about HA dissociating to the H plus ion and the A minus ion. This down here is the same thing as this up here. I'm just not including that extra water molecule. And I prefer that because then it makes a little bit simpler expression for our Ka down here. HA is aqueous, H plus ion is aqueous, and A minus ion is aqueous. So the K expression for this reaction, again, will be H plus times A minus over HA. Now, a little bit more of a review. Jace, if I say, or actually I think it's Brielle's turn. Brielle, if I say that the K for this acid equals 300, what does that number mean with respect to this equilibrium expression? Do you remember?
That value is number where there's that equilibrium between the products and the reactants.
Very good. That's right. And what would that mean for, let's say I have a different acid here, which I'll call HAX. Whoops, a little bit lower here. That does the same thing, H plus, AX, but this K here equals 0.2. What does that mean if this one equals 300 and this one equals 0.2? What are that value generally telling us? Do you remember, Brielle?
Like, if it's a higher number, usually there's more of the products than the reactants, and if it's lower, then there's more of the reactants than the products.
Very good. Very good. Now, in terms of acids, in terms of these two acid compounds that I've drawn here, what does that tell us about these acids in terms of their strength? Can we know anything about the strength of HA and the strength of HAX relative to each other?
I am not sure.
Okay. Well, remember, when we talk about strength of acid, all it's really meaning when we say this acid is strong is the amount of dissociation that actually occurs. So if K is a large number like 300, it means that at equilibrium, the concentration of the products is going to be relatively high, whereas if the equilibrium for this reaction down here is 0.2, that means that this HAX is going to be more prominent than the dissociated species. So the larger K value also corresponds to the stronger acid, meaning more of it is going to be towards products for the K equaling 300 as opposed to K equaling 0.2. All right, now I'm going to also put a little K, a little tiny A right there to remind us that this is the K of an acid, and that's what the little Ka means. It's just telling us that it's just really reminding us, because it doesn't need to be there. We can see that this is the equilibrium, and that's the K value, but we want to make sure you're not confused by when it says Ka or Kb or Ksp or whatever. It's just a K like normal, but for this we're talking about the material acting as an acid. All right, so Kas are constants for acids, and the larger the Ka, the stronger the acid. The lower Ka, the weaker the acid. Kb's are exactly the same thing, except for it's not about an acid, it's about the compound behaving like a base. So when you have a base, it takes a proton away from something. So B becomes BH plus, and it removes it from water and results in the hydroxide ion, for example. That process, that base dissociating the water, right, can be defined as a Kb. Again, products over the concentration of products over the concentration of reactants will be our Kb. All right. The negative log of the Kb is pKb. That's also something we didn't talk about here, but the negative log of the Ka is the pKa. All right. And that is a special pH, which we'll talk about in a bit. Okay. Now, a quick little review here. If we're looking for the product in the ionization of a given acid, remember, if this thing is behaving as an acid, H2CO3, essentially what we're asking it to do is donate a proton. So whenever we're told that a given compound is an acid, then that means it's going to donate a proton, and the rest that's left behind is going to be known as the conjugate base. Okay? So in that, whenever we're given anything, even if it doesn't look like an acid to us, if we're told it behaves like an acid, then it's just going to donate a hydrogen. This is another reminder. There's a relationship between the strength of the acid and the strength of its conjugate base. If the acid is very strong, the conjugate base is very weak. All right? So because of that, we have another relationship which we can utilize when we need it. And it's that Kw, which is the negative log of 1 times 10 to the minus 14, right? Kw equals the negative log of Ka plus the negative log of Kb. Let me pull this up a little bit. Or another expression here, Kw, 1 times 10 to the minus 14, equals Ka, right? Whatever the Ka is, not the negative log, just the Ka, times the Kb of the conjugate base. All right? So two important equations that we can use. Hopefully this isn't blowing your mind terribly. It's basically the same as we've seen before, that 14, and that's what negative log of this is, right? Negative log of 1 times 10 to the minus 14 is 14, is equal to POH, or pH plus POH, right? Basically seeing the same thing, where instead of taking the negative log of the hydrogen ion concentration, we're taking the negative log of our equilibrium constant for our acid and the negative log for the equilibrium concentration for the base. So we'll use these tools moving forward to identify the pH, POH, hydrogen ion concentration, hydroxide ion concentration of different solutions. So, what's the value of Kb for the following, what is the value of Kb for the following weak conjugate bases? All right, so here is sodium fluoride, and we're told that the Ka for hydrogen fluoride, the Ka for HF, is 6.8 times 10 to the minus 4. 6.8 times 10 to the minus 4. All right. Well, we know that the Ka for the HF times the Kb for its conjugate base. Now, what's the conjugate base of HF, Jace? Do you know what the conjugate base of HF is, Jace? Any ideas, Alyssa? What's the conjugate base of HF?
F minus.
F minus. Very good. So the Ka of HF times the Kb of F minus will equal the Kw. Kw. Do you remember, Alyssa, what Kw equals? What does that W stand for?
Is it water? Okay, it's water. So that's a constant 1 times 10 to the negative 14.
That's right. All right. So because we know 1 times 10 to the 14 is always going to be the product of the Ka and the Kb of a compound, and here they gave us the Ka for this acid, 6.8 times 10 to the minus 4. We can solve for our Kb simply by taking 1 times 10 to the minus 14 and dividing it by the Ka. Okay. Sodium cyanide, if we have a Ka for HCN, what is the conjugate, or what is the Kb for the Cn minus ion? What do you think, Brielle? How do we do this?
Okay, so it would be Ka of HCN times Kb of Cn minus.
Very good. And that would equal what?
I would need to solve it. Okay.
Well, I mean, the Ka times the Kb would equal Kw.
Oh, the Kw, so it would be 1 times 10 to the negative 14.
Right. Very good. So we got 1 times 10 to the minus 14 divided by our Ka, 6.2 times 10 to the minus 10, and that's going to be our Kb for the conjugate base of HCN, which is the cyanide ion. Cyanide ion. All right. So here we're told that the Kb for ammonia is 1.8 times 10 to the minus 5, and we're asked what is the Ka for the following weak conjugate acids. So if this is a conjugate base, NH4, the conjugate acid is going to be, Kb is going to be NH3, the conjugate acid is going to be NH4, and we'll solve for Ka simply by taking, again, 1 times 10 to the minus 14 and dividing it this time by 1.8 times 10 to the minus 5. Okay, so here we have a compound. We might not be able to recognize this as an acid very well, but as soon as we're told the Kb for this compound, all we have to do is take Kw again, divided by Kb, and it'll give us the Ka for the conjugate base, or conjugate acid of this base. All right, I think that is where we're going to stop for today. So, if anybody has any questions, let me know. Otherwise, we will meet again on Wednesday. Any questions?
I just had a question about the last lecture.
Yeah.
Was it on chapter 16?
Was it on chapter 16?
Yes.
Yeah.
Okay, because I looked back at the lectures on chapter 15 and I had already seen those. Okay, that makes sense. Thank you.
Yeah, let me double check here. Did you, I mean, maybe I didn't update the link correctly. If you go into this homepage here and look for course materials.
There's one that's acids and bases revisited. Is that the whole lecture?
Yeah, that's it.
Okay, awesome. Sorry, I was just confused.
That's fine.
Thank you.
You bet. Anything else? Okay. Thank you, guys. Talk to you later.